Section 2. Valuation Approaches. In this section, we will introduce both the full and the local approaches for the valuation of VAR, and our focus is on the local approach. The profit and loss of a portfolio can be attributed to two sources, the exposures and the movements in risk factors. For the first, asset positions can be replaced by their linear exposures to the risk factors, or their quadratic exposures, or by using full pricing models. For the second, the distribution of risk factors can be modeled using a normal distribution or historical data or Monte Carlo simulation runs. Finally, the dollar value of asset positions can be replaced by a set of dollar exposures on the risk factors, which are aggregated across the entire portfolio. Let's first introduce the full valuation. Suppose an asset's value is dependent on a single risk factor S, then its value at the initial time, denoted by V0, depends on S0, and its value at the risk horizon, denoted by VH, depends on SH. The profit and loss, denoted by delta V, is equal to the asset's value at the risk horizon minus the asset's value at the initial time. Full valuation methods involve an explicit evaluation of VH for a wide range of risk factor values at the risk horizon in order to obtain delta V. The values of SH can be generated by simulation methods, such as the historical simulation or the Monte Carlo simulation. In the following, we will focus on the local valuation. Local valuation methods involve the use of partial derivatives with respect to the risk factors. As an example, the profit and loss, namely the change in the asset value V, can be approximated by the first-order partial derivative of V with respect to the risk factor S, evaluated at the current position, times the change in the risk factor S. The first-order partial derivatives of V with respect to the risk factors, evaluated at the current position V0, would be called delta for a derivative, or modified duration for a bond portfolio. Such local valuation methods are called delta normal methods if they assume further that the risk factors are normally distributed. As an example, consider a long position on a netted money call with delta 0 equal to half. Then, its potential loss can be approximated via the formula given in the previous slide. That is, delta 0 times the change in the underlying asset price S. Alternatively, this can be rewritten as the product of the dollar exposure, delta 0 times S, and the rate of return in S. And in this case, we treat the rate of return in S as the risk factor. If the distribution of the rate of return in S is normal, and sigma is the corresponding standard deviation, then the VAR of the option can be estimated by the following formula. Now let's take a look at an example. Consider a portfolio consisting of options on companies ABC and XYZ. The option on ABC has a delta of 100, and the option on XYZ has a delta of 2,000. The ABC share price is $12, and the XYZ share price is $3. Suppose that the daily volatilities are 1% and 2% for ABC and XYZ respectively, and the correlation between the daily changes is 0.6. Can you obtain the 95% one-day VARs of the two individual option positions and for the portfolio of both options? The change in the value of the option positions on ABC in one day is given by the following, where 12 times 100 is the dollar exposure of the option position, and delta S1 over S1 is the rate of return of the underlying ABC stock. Similarly, that of the option positions on XYZ can be calculated as follows. In the above expressions, delta S1 over S1 and delta S2 over S2 are the proportional changes in the prices of ABC and XYZ respectively, and they are where the risk lies in. Thus, the individual 95% one-day VARs for the two option positions can be calculated respectively as follows. Note that for 95% confidence level, alpha is equal to 1.645. For the portfolio, we have the change in the portfolio value equals to the sum of the changes in the value of the two options. Then, the variance of the change in the portfolio value can be calculated as follows, where the first and the second terms are the variances of the changes in the values of options on ABC and XYZ respectively, and the third term is twice of the covariance between the two. Therefore, we get the following 95% one-day VAR of the portfolio. For nonlinear V, one can improve upon the quality of the linear approximation by adding more terms in the Taylor expansion of V. In the earlier example, we could add the second-order term, which gives rise to the delta-gamma method. For an option, we will write in this form, where gamma 0 denotes the second-order partial derivative of V with respect to S at the initial position V0. Assuming the rate of return in S is normal, then we could approximate the VAR of the option with the following formula. Note that VAR is reduced as compared to that obtained by the delta normal method when gamma is positive, and increased if gamma is negative. That is the end of the section on the valuation approaches. Next lesson, we'll focus on the delta normal method for estimating VAR of portfolios with multiple risk factors.